Welcome back to the lecture series on data structures. In this lecture, we talk about breadth first search algorithm. For this, we need certain concepts of spanning trees from the graph. Let G is equal to V comma E be a graph. Then a spanning tree is a subgraph of graph G such that the subgraph should consist of all the edges of the G, but regarding the number of edges, it should contain only those edges which do not create a cycle. So the given graph should be connected, and if we can extract a subgraph of G such that it contains all the vertices of G and do not contain any cycle, such a subgraph is called a spanning tree. In this example, we have 4 vertices are there and 6 vertices are 6 edges are there. From this, we can observe that there are several possible spanning trees are there. Here are some of the examples of spanning trees that are being constructed from the given graph. 4 vertices are there in each of them, and no cycle is present in any one of them. So these are all the possible spanning trees that we can generate from the given graph. Given a graph, how to construct a binary search tree from the graph is a problem here. We can solve this problem by using two methods. One is breadth first search method and another is depth first search method. Now we look into the breadth first search method here. Given a graph, if we start at a vertex, treating it as level 0, all the vertices which are adjacent to it will be treated as level 1, and those vertices which are adjacent to the vertices at level 1 will be treated as level 2, and so on. Now if we look at the graph in such a way, if we start at the vertex A, that is at the level 0, the immediate set of vertices adjacent to B and C or to A, then at level 1 B and C will be added to the spanning tree, so that the edges AB and AC will be added to the spanning tree. And then at the first level, B and C are the vertices. At B, there is one vertex adjacent to that, and addition of that edge should not create a cycle with the existing edges of the spanning tree. So if I add BD, it is not going to create any cycle with AB and AC, so I can add BD. Similarly, at level 1, C is also a vertex present, and I can add edge CE. Of this, if I add CE, it is not going to create a cycle. So I can add any of the edges DE or CE. So for that matter, we can choose the ordering among the vertices here, so that I can add C comes first, so I'll add CE. If I add CE, then I cannot add DE, because if I add DE at D, it is going to create a cycle with the existing edges. So I can't add DE. So moving forward, at level 3, E is present, and only one vertex is present at level 3. Now, 3 vertices are adjacent to level vertex E, and L, F, G are the vertices. So add those edges, and again adding of those edges is not going to create a cycle. Then come to level 4. At L there is no edge. At F and G we have 2 edges. Again at F comes first, so if I add the edge, then it's not going to create a cycle. But after adding this FH, if I add an edge GH, it is going to create a cycle, so I don't add GH. Then going to the next level, at H, I have 3 edges incident on it. HI, HJ and HK are the edges incident on H. So again, adding of these is not going to create a cycle, so I can add them. At I, J and K, I don't have any edges further, any vertices incident on that, so the algorithm stops here. And by this time, all the vertices are traced and the tree do not contain any cycle. So this is going to create one BFS tree. If we change the order of the vertices, obviously the tree that is going to be constructed will change. Similarly, the order in which we consider the vertices is also very important here. If we start constructing the tree at a particular vertex, then the tree will be different. So there are several possible trees that can be constructed. This is one such tree. Now we look into the tree traversal algorithm with respect to breadth first search in the given graph. To implement this process, we'll initialize with a starting vertex v for a given graph. And if you remember in the previous example, at any stage we are considering the vertices that are adjacent to the current level of vertices, and we're tracing them to the next level. So now to keep track of this, here we need to initialize a queue here, and to avoid the addition of cycles, we need to observe whether the already existing edges are creating a cycle or not. To observe this, we are initializing an array which is having a status as visited, whether the vertex is already previously visited or not. To observe this, we are initializing an array. So Q is there and initialized array with the flags set as 0 initially. So initially no vertex is visited. Now for the first time we'll initialize the Q with the starting vertex v, so nq q comma v, and set the visited status of v as 1. After this, stage by stage we visit all the vertices level by level. So while q not equal to empty, keep on doing this. What is that? dqv, whatever the first in first out type starting vertex is there, then that has to be dequeued from the queue. That means that is to be processed. Once that is dequeued, print that vertex. That means that vertex is traced. While doing this, add all the vertices which are adjacent to v to the queue. So for all vertices u adjacent to v, if visited status is 0, then nq q comma u. So add those vertices to the queue which are not visited so far. That means the visited flag is 0. So then set visited u is equal to 1. Once it is visited, then added, then set visited u is equal to 1. So to keep on doing this in the while loop until the queue is empty. That means stage by stage we'll be keep on adding the vertices, and if they are already visited, we ignore them, and if they are not visited, again the corresponding edges will be added or traced. Vertices are traced. So like this, all the vertices are dequeued. We need to keep on traversing through the queue. Let us try to implement the algorithm that we have seen in the previous slide here on the example. The initially queue will have vertex A. The starting vertex is taken as A, and visited flag of that A is 0, set as 0, and all the remaining vertices are having visited flag as 0. Then dqa, that's the first step. So print A. Once it is printed, immediately we need to push the vertices that are adjacent to A. B and C are the vertices that are adjacent to A. So push them into the queue B comma C, and make the vertices flag as visited in the visited flag array 1 comma 1. And once BC is added, the first element is to be dequeued, B is dequeued, and print B. And while doing so, the vertices that are adjacent to B are added here, D is added, and make the visited flag of D as 1. And the latest element is C, so print C, dequeue that, and the vertex that is adjacent to C is E, that is added into the queue. Again, visit flag of E as 0, so 1. The latest element is D now, print D, and the vertices that are adjacent to D are E, which is already marked as visited, so no new vertex is added here. Then if we the next element is E, print E, then the vertices that are adjacent to E are L, F and G are added here, and the corresponding flags are set as 1. Again, latest element is F, print F, and the vertices that are adjacent to it is H, make flag of H as 1, and H is added. Again, latest element is L, and no new vertex is added to that, and the next element is H. H has to be printed, and I, J, K are added to the queue, and corresponding flags are set as 1. And then latest element is I, print I, no new vertex is added, all the vertices are flagged as 1. Print J, again no new vertex is added, print K, no new vertex is added. By this time Q is empty. So in the previous slide, if you look at the while loop, while Q not equal to empty, the algorithm runs. So here the Q is empty, algorithm stops here. so that by this time all the vertices of the binary search tree in the given graph are traced in the sequence of print A, print B, print C, print D, E, F, G, L, H, I, J, K. This is a sequence in which the verses are traced. Thank you for watching. If you like the video, you can share it with your friends so that majority of the students can be benefited.